Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the Euler's critical load for a column with one end fixed and other end hinged. Now, in this case, the column is fixed at one end and hinged at the other end, or you can say one end of the column is fixed in position and direction, and other end is fixed in position only. Now let us take a section at a distance x from the fixed end. Now the lateral deflection due to buckling is y. Now as the column deflects like this, there will be a resisting moment against this deflection. So because of this buckling, the fixed end will exert a resisting moment to make the column straight, to prevent this buckling. So this is a resisting moment formed at the fixed end. The hinged end cannot do that. Okay, when column buckles and slope will not be zero here at the hinged end, but at the fixed end slope will be zero and there will be a resisting moment exerted at the fixed end. Now if you go for the summation of moments, this resisting moment formed at the fixed end should be opposed by any other moment, so that the total summation of the moments will be zero. The total summation of the moments should be zero. So there is a moment formed. You understood that there is a moment formed, resisting moment, reaction moment formed at the fixed end, but there should be a opposite moment formed by some other forces which balances this moment. Otherwise this moment m alone cannot exist. So at the ends this can exert only a force. Okay, so there is a vertical force, the load applied, and there also will be a horizontal reaction and two reactions at the fixed end. There is a vertical reaction and also there will be a horizontal component of reaction. This horizontal reaction here and this will form an anti-clockwise couple which will oppose this clockwise couple. So there will be a horizontal reactions at both the ends. So that horizontal reaction, if you take it as R into the L, the moment produced by that horizontal reactions R into L should be equal to M. So M or plus M minus R into L is equal to 0, or M should be equal to R into L. So you can relate the resisting moment here or reaction moment here with the reaction R formed at the horizontal reaction R formed at the ends, as M is equal to R into L. There will be a vertical reaction which will be equal to the applied load P. So this is the vertical reaction, and horizontal reaction and moment at the fixed end are related by M is equal to RL. Now let us write the differential equation for the deflected curve. EI d square by dx square is equal to total bending moment acting at that section. Now the bending moment at this section is plus M minus Py. P is producing an anti-clockwise moment. This is clockwise moment, plus M minus Py, and there is one more force, horizontal force, this into x distance, that is a moment produced, and it is also anti-clockwise, so minus Rx. This is R into x, so plus M minus Py minus Rx. So that is the total moment, bending moment acting at this section. So EI d square by dx square is equal to M minus Py minus Rx. M you can replace as RL. So RL minus Py minus Rx. You can write it as R into L minus X minus Py. Now minus Py I take left hand side. EI d square by dx square plus Py is equal to R into L minus X. Now dividing by EI, we will get d square y by dx square plus Py by EI is equal to R into L minus X divided by EA. Or this right hand side you can write it as P by EA into R into L minus X by P. So I am just introducing P in the numerator and denominator. So it is equal to this only. P cancels, you are getting the same quantity. So I am just writing it in terms of P by EA. P by EA into R into L minus X divided by P. So you are getting the differential equation as d square by dx square plus P by EAy. P by EAy is equal to P by EA into R into L minus X by P. If you substitute P by EA as m square, you will get the differential equation as d square y by dx square plus m square y is equal to m square. P by EA is m square into R into L minus X divided by P. We can write the solution for this differential equation as y is equal to C1 cos mx plus C2 sin mx plus R into L minus X by P. That will be the solution for the differential equation. So solution is y is equal to C1 cos mx plus C2 sin mx plus R into L minus X by P. Now if you differentiate, you will get the equation for slope. So dy by dx is minus C1 m sin mx plus C2 m cos mx. The differentiation of this is, so for this if you split, you will get two parts, RL by P and minus RX by P. RL by P is a constant part, differentiation is 0. Minus Rx by P, when you differentiate, you get minus R by P. So you are getting dy by dx is minus C1 m sin mx plus C2 m cos mx minus R by P. And we know when x is 0, the slope of the deflected curve is 0. So initially the column remains straight because of the reaction moment exerted by the fixed end. So when x is 0, dy by dx is 0. So putting that condition, dy by dx is 0, then x is 0. So this part is 0, dy by dx is 0, then x is 0. C2m, okay, C2m minus R by P. C2m minus R by P is equal to 0, or you get C2m as equal to R by P, or C2 as R by Pm. So you are getting the constant C2 as R by Pm. So the constant C2 is R by Pm, and you can write down this equation once again. Y is equal to C1 cos mx plus, instead of C2, R by Pm sin mx plus R into L minus X by P. So solution is after substituting C2. So in this again we know another condition here at this end, x is 0, y is 0. So we will put this condition in this equation. So y is 0 when x is 0. So cos 0 is 1, so you get C1, and sin 0 is 0, so you get this part 0. When x is 0, you get RL by P. So C1 plus RL by P is equal to 0, or you get C1 as minus RL by P. So you are getting the other constant. So you got the other constant C1 as minus RL by P. Now you can substitute C1 also here. So you can write down this equation again. Y is equal to minus RL by P cos mx plus R by Pm sin mx plus R into L minus X by P. Now last condition which is known, when x is equal to L, deflection is 0. When x is L, that is here, y is 0. There is no deflection, it is fixed in position, so y is 0. X is L, y is 0. So putting that condition, y is 0 when x is equal to L. Minus RL by P cos ml plus R by Pm sin ml. When x is L, this term will be 0. L minus L, 0. So you get this equation. when you divide by r by p cos ml, so r by p cos ml cancels, you get minus l plus r by p cos ml when you divide here, so you get tan ml by m. So tan ml by m minus l is equal to 0, or tan ml is equal to ml. Tan ml is equal to ml. So tan ml to be equal to ml, tan of a quantity is equal to that quantity itself. That quantity should be approximately equal to root 2 pi. It should be approximately equal to root 2 pi. Okay. Or m is root of p by ei into l is equal to, I will just equate that, I will take it as equal, approximately equal, so but I will take it as equal. So root of p by ei l is equal to root 2 pi, squaring it, p by ei l square is equal to 2 pi square, or p is equal to pi square ei by l by root 2 square. So rearranged in this form, p is equal to pi square ei, so that all the denominator are getting pi square ei divided by l by root 2 square. So this is the buckling load for a column with one end fixed and other end hinged. In general, the buckling load for a long column with the different end conditions can be written as P is equal to pi square ei by L square, where L is the effective length of the column. So you can write in this standard form as pi square ei by L square. The crippling load or buckling load for a long column is pi square ei by L square, where L is effective length of the column. It's capital L I used. L is effective length of the column, and this L can be substituted based on the end condition. When both ends are hinged, that effective length is equal to length of the column. So you get pi square ei by L square. When both the ends are fixed, you can substitute L as length of the column divided by 2, L by 2. So you get L by 2 square. When one end is fixed and other end is free, effective length is twice the length of the column, or 2L. So it is 2L square. When one end is fixed and other end is hinged, effective length is length of the column divided by root 2, L by root 2 square. So only this you have to remember, and general formula. Standard formula you can remember as P is equal to pi square ei by L square, where L is the effective length. Effective length you can substitute as L by 2, 2L, or L by root 2 based on the end conditions. So when both ends are hinged, effective length is equal to L. Both ends are fixed, effective length is half of the length of the column. When one end is fixed and other end is free, the effective length is twice the length of the column. And one end is fixed and other end is hinged, effective length is length of the column divided by root 2. There are certain assumptions we have made in the derivation of Euler's formula. So we assume that load acting is collinear with the axis of the column. Stress induced in the material of the column is within the elastic limit. The stress induced, we assume, that is within the elastic limit of the material. The column is perfectly straight and its self weight is negligible. So column is assumed to be perfectly straight and weight of the column is neglected in calculating this buckling load. We assume that it is negligible compared to the effect produced by other parameters. Now material of the column is assumed to be homogeneous and isotropic. So these are the certain assumptions we made in the derivation of Euler's formula for the buckling of long columns. That's all for today. Thank you for watching.